Hello everyone and welcome. Today I want to invite you on a journey into the hidden world of microchips. A world we don't often see, yet one that's quietly powerful so much of our lives. Chips are at the heart of every piece of modern technology, from the phone in your hand to the supercomputers advancing medicine and science. But behind each of these chips lies a process that almost mystifies in its complexity, and it's no exaggeration to call it an art form. I'm Gladwin Rosario, a computer engineering technology student at the Polytechnic University of the Philippines Institute of Technology, and in this video, we'll explore the inquiries to learn where the direction of chip manufacturing is heading. I invite you to reflect on how far we've come as we go into the world of computer engineering. Let's begin! Chip manufacturing starts with something as simple as silicon, found abundantly in the sand. It's humbling to think that these tiny grains of sand are the foundation for the devices we rely on every day. From smartphones to advanced computing systems, silicon undergoes a rigorous purification process, transformed into smooth, reflective wafers. Imagine this as blank canvases, eagerly waiting the artistry that will turn them into powerful and purposeful components of technology. Each wafer embarks on an incredibly intricate journey through the manufacturing process. First, there's doping, where we customize the electrical properties of silicon, creating precise pathways for electricity to flow. Following this, deposition and etching shape these pathways, adding layers upon layers of material, each step being as closely to a fully formed chip. It is a through reweaving an invisible web of circuits, layer by layer, ensuring that every connection is perfectly aligned and ready for action. And perhaps the most awe-inspiring aspect of this process is photolithography. In this stage, advanced lasers are employed to project intricate patterns onto the silicon, mapping out the tiny highways that electrical signals will traverse. These clean rooms where this magic happens are cleaner than any other environment on Earth. Even a single speck of dust could spell disaster for an entire wafer. This attention to detail is a testament to the perfection demanded in this industry, a level of precision that pushes technology to its absolute limits. It's remarkable to consider that something so small and seemingly simple can be crafted with such care and complexity, representing the pinnacle of human ingenuity and innovation. With all these steps in mind, it might seem obvious that chip manufacturing is challenging, but what's less obvious is how many barriers we face in perfecting this intricate art. The scale alone is hard to fathom. We're dealing with features measured in nanometers. A single transistor is around 3 nanometers wide, far smaller than the width of human hair. To put it in perspective, that's roughly around 1,000 times smaller than the diameter of human red blood cell. Working at such a tiny scale requires absolute perfection. Even the slightest deviation can render a chip non-functional. Every layer, every pattern has to be flawlessly aligned, and the margin for error is virtually non-existent. Then, there's the machinery involved. Photolithography machines, which are crucial to this process, are among the most advanced technologies in existence, costing upwards of $200 million each. These sophisticated tools embody decades of engineering, innovation, and representing the cutting edge of our capabilities. Yet, even these machines must evolve constantly as we strive to meet the surging demand for faster, smaller, and more efficient chips. But it is not just about machinery. We also need rare and special materials. Metals and compound sourced from all over the world are essential in chip production. Even the global chip shortage has highlighted just how fragile and interconnected these supply chains can be. When any part of this chain is disrupted, it can have significant ripple effects throughout the industry. And let's not forget about the environmental impact chip manufacturing consumes. Incredible amounts of energy, often enough to power entire cities. The process involved generates substantial waste and byproducts, raising important questions about sustainability. As we push forward in innovation, finding ways to minimize this impact and create more sustainable practices is becoming an increasingly critical part of the story. Of all the steps in chip manufacturing, photolithography might be the most mesmerizing. Imagine it as a form of high-tech printing, but a scale that seems almost magical. With light and a carefully crafted stencil, known as a mask, we project intricate circuit patterns onto the silicon wafer, transforming blank surfaces into complex network of functionality. To achieve the tiny sizes we need, we employ EUV or extreme ultraviolet light. EUV is significantly shorter wavelength than visible light, allowing us to create much finer details in our circuit designs. It's incredible to think that each time we print a circuit pattern onto silicon, we're drawing lines smaller than a virus particle. Navigating a scale where unconventional methods would fail. The precision required in this process is extraordinary. Each alignment and exposure must be meticulously controlled to ensure flawless results. And these EUV machines are marvel of engineering in their own right. They're some of the most advanced pieces of technology ever created, representing billions of dollars in research and development. Their intricate design and functions are the culmination of years of innovation, pushing the boundaries of what we thought was possible in manufacturing. In many ways, photolithography encapsulates humanity's relentless pursuit of the impossible. We're crafting photography so precise that it operates the very edge of what physically appreciable, redefining the limits of miniaturization and in performance in a digital age. This process not only fuels the growth of technology, but also inspires us to continually reach for new heights in innovation. So, after all these intricate steps, how do we end up with a working CPU, the brain of every modern computer? After the process of etching and doping, we're left with billions of tiny transistors in each chip. Each of these transistors functions as a switch that controls the flow of electricity, essentially flipping on and off to represent binary data. It's a beautiful concept. These minuscule switches work in concert, allowing the CPU to process data and perform calculations at astonishing speeds, making it possible for our devices to run complex applications seamlessly. The wafer, now densely populated with these intricate circuit patterns, is cut into individual dies. Each die becomes a separate chip, but all chips are created equal. After rigorous testing, only those that meet the highest performance and reliability standards become high-end CPUs. The others, which may still function well, might be used in less demanding devices, showing the remarkable versatility of technology. It's fascinating to think that each die could yield a significantly slightly different outcome. Each one is a unique result of the delicate balance achieved during manufacturing. Even the smallest variations in the process can influence performance, efficiency, and power consumption. This variability underscores the complexity and majesty involved in creating these essential components of modern technology. As we look to the future, the world of computer engineering is filled with promising and transformative trends, each shaping our vision of what technology can be. AI and machine learning are leading the way, driving advancements we could only dream of a decade ago. With chips that can handle massive calculations in milliseconds, we're now capable of developing smarter algorithms and even autonomous systems. Then there's the potential of quantum computing. By using qubits instead of traditional bits, quantum computers can process information in ways we're only beginning to understand. Imagine solving complex problems in seconds that would take classical amounts of computer years. And let's not forget about edge computing and the Internet of Things. These technologies are reshaping the way we think about data, bringing processing power closer to where it's needed most. From wearables that monitor our health in real time to smart cities, these advances are poised to change how we live, work, and interact with the world. Finally, as the world becomes more aware of environmental issues, sustainable technology is emerging as a critical focus. Chip manufacturing, as we've seen, is energy intensive, and the industry is now pushing for greener, more efficient methods that lessen the environmental footprint of our technology. When we look at the journey of microchip, from raw silicon to the final product powering our technology, it's a reminder of what humanity can achieve when we combine creativity, science, and sheer determination. Each chip is a testament of years of research, billions of dollars of investment, and an unwavering pursuit of perfection. In the future, as new trends of technologies emerge, it's exciting to think of how they'll continue to shape not only the computer engineering, but also the world we live in. Thank you again for joining me on this exploration. If this reflection resonated with you, feel free to share your thoughts as we go to the world of beauty engineering. Which part of microchip computer or computer engineering inspires you the most? And until next time, I'm Gladwin Rosario, and let's keep appreciating the tiny marvels that power our world.